What if that empty bottle in your trash could return as a breathtaking chandelier worth hundreds of times more? But here's what nobody tells you. Ordinary bottles can become the raw material for extraordinary decorative glass. Imagine thousands of bottles arriving dirty, scratched, and mixed together before machines and human eyes decide their second life. First comes separation, because the wrong material can ruin an entire batch once those bottles enter the furnace. And this is where it gets truly extraordinary. Glass can be recycled repeatedly without losing its basic material identity. Most people never think about this, but recycled glass can replace part of the virgin material normally needed for new glass. Europe alone collects roughly 8 out of 10 glass containers for recycling, showing how powerful this loop can become. Yet recycling begins long before the furnace. It begins with collection systems designed to keep glass clean and separate. The bottles may come from homes, restaurants, bars, hotels, shops, and collection centers across surprisingly long supply chains. Their colors matter too, because clear, green, and amber glass can require careful sorting before decorative production begins. But bottles are never simply thrown into a furnace. First, contaminants must be removed with surprising precision. A tiny ceramic fragment may sound harmless, but inside molten glass it can create serious defects and weak spots. Once cleaned, the bottles become cullet, a simple word for a remarkably valuable ingredient in glassmaking. And every ton of recycled glass can avoid roughly 1.2 tons of virgin raw material extraction. The cleaned cullet now faces its most dramatic transformation yet, heat powerful enough to erase its previous shape completely. Think about it. Yesterday's bottle still contains the same basic glass chemistry needed to become tomorrow's decoration. Most beverage bottles use soda-lime glass, commonly based on silica, soda, and lime in carefully controlled proportions. Recycled bottles do not magically become laboratory-grade crystal. This process creates decorative glass with a crystal-like appearance. Hat distinction matters, because true lead crystal and recycled soda-lime bottle glass are not the same material. Now imagine the sorting table, thousands of fragments, every color and shape waiting for a machine to decide. Optical systems can identify differences in color and material while air jets rapidly eject unwanted pieces. The sound changes here too, from clattering bottles to a steady mechanical rhythm of belt crushers and sensors. Then the crusher changes everything, breaking whole bottles into controlled fragments that flow far more efficiently. Those fragments must remain clean, because trapped ceramics, stones, metals, or organics can cause trouble later. What happens next surprised even experienced engineers. The tiny pieces become easier to melt because they already possess glass structure. Industry data shows increasing cullet can reduce furnace energy demand, making recycling valuable beyond simply saving bottles. Vive reports that every 10% increase in cullet can reduce furnace energy consumption by about 2.5%, and 1 ton of recycled glass can avoid about 580 kilograms of carbon dioxide emissions compared with virgin production. But now comes the dangerous-looking part. Thousands of glass fragments are about to enter temperatures above 1400 degrees Celsius. Bottles have disappeared forever, but their material is only seconds away from becoming something completely new. Industrial glass furnaces commonly operate around 1400 to 1600 degrees Celsius, depending on the glass process inside. Heat dissolves the old fragments into a homogeneous molten mass, while gases and impurities must be carefully controlled. Now the liquid glass must leave the furnace at exactly the right moment, neither too fluid nor too stiff. For chandelier production, artisans can form recycled glass into drops, beads, petals, discs, rods, or sculptural decorative pieces. A glassblower may gather a measured amount on a heated metal pipe, then rotate it continuously to control shape with controlled air and gravity. The hot material stretches, rounds, and transforms under the artisan's smallest movements. But a chandelier needs repetition, so every component must visually reaches a single unfinished pendant. That's why molds, gauges, templates, and experienced hands work together to keep shapes remarkably consistent. Then comes annealing, one of the quietest steps, yet one of the most important for preventing internal stress. Rapid cooling can create dangerous stress, so the pieces cool gradually through a carefully controlled temperature range. For fused glass, annealing schedules vary with thickness and composition, so there is no universal temperature recipe. Once cooled, the pieces become stable enough for cutting, grinding, polishing, drilling, and detailed finishing. Diamond abrasives can smooth sharp edges and refine surfaces without hiding the glass's natural character. And this is where recycled glass begins looking surprisingly luxurious, because geometry can amplify light without changing the material itself. But before assembly, every piece must survive inspection, because one hidden crack can become a failure later. Inspectors look for chips, cracks, bubbles, inclusions, dimensional errors, and surface defects before assembly ever begins. A laser scanner can also compare geometry against a digital reference, catching dimensional differences invisible to the naked eye. The machine sees coordinates and tolerances, while the human inspector notices something harder to measure. Beauty hat judgment matters because recycled glass naturally carries subtle variations that can make each handmade piece feel alive. Now the separate pieces are ready to become one chandelier, but the engineering challenge is only beginning. Every pendant needs secure attachment, balanced spacing, and carefully routed electrical components hidden behind the visual spectacle. Balance becomes critical as dozens or hundreds of glass elements pull downward from the same central structure. Engineers calculate load paths while craftsmen adjust spacing by fractions, creating symmetry that machines alone cannot fully guarantee. Then the lights switch on, revealing whether every polished surface catches the illumination exactly as the designer imagined, and suddenly, the factory floor disappears beneath reflections, colors, shadows, and thousands of moving highlights. But here's the hidden challenge. Beauty means nothing if the chandelier cannot safely support its own weight. Engineers inspect mounting hardware, attachment points, electrical routing, and structural connections before the chandelier leaves the workshop. Automated vision systems can scan surfaces quickly, searching for chips, cracks, scratches, and irregularities under controlled lighting. Sensors measure position and geometry, but lighting tests reveal something equally important: how the finished glass actually behaves. A perfectly measured piece can still look wrong if its facets scatter light differently from the surrounding pieces. This is where human craftsmanship can beat automation, because an experienced eye understands proportion, reflection, and visual harmony. The rejected pieces aren't automatically worthless. Depending on condition, they can return to the recycling stream. Again, that's the beautiful irony of glass. Even a failed decorative piece can become feedstock for another glass-making cycle, but the loop only works when collection, sorting, melting, forming, finishing, and assembly all cooperate perfectly. One weak link can increase waste, energy use, defects, transport, or the time needed to finish each piece. Modern factories therefore connect sensors, cameras, process controls, and human decisions into one continuous production system. Yet automation doesn't eliminate craftsmanship. It gives skilled workers better information while they make the final visual decision. Every chandelier eventually becomes a conversation between precision engineering and deliberately imperfect human artistry. Now imagine hundreds of these components arriving together, each one needing a precise place within the final pattern. Workers follow layout drawings, match shapes, adjust heights, and repeatedly step backward to judge the chandelier from a distance. That repeated step backward may look simple, but it catches a symmetry that close-up measurements can miss. And then comes the moment everyone waits for: the final illumination test. One switch, and discarded bottles become hundreds of glowing surfaces, turning waste into an object of desire. And this tiny workshop sits inside a much larger world. Global glass production reaches enormous industrial scale every year. Recent industry estimates place worldwide glass bottle and container production around 830 billion units in 2024. That's roughly enough containers to imagine filling enormous cities with glass. Before recycling brings some of them back, around the global glass manufacturing market was estimated around $235.8 billion in 2024. Behind those numbers are furnaces, drivers, recyclers, engineers, artisans, designers, technicians, and countless supporting workers. Europe alone has more than 100,000 direct and indirect jobs connected with its container glass ecosystem. Europe's glass collection rate has reached above 80%, with the industry targeting 90% by 2030. That target matters because better collection means more clean cullet. And more clean cullet means less virgin material extraction. Did you know 1 ton of recycled glass can save about 1.2 tons of virgin raw materials? Did you know glass can remain in a recycling loop? repeatedly without losing its fundamental glass properties. And did you know recycled cullet can reduce melting energy because the furnace doesn't start with raw minerals alone, but recycling has limits too? Contamination, collection losses, transport, energy use, and unsuitable glass mixtures can complicate the loop. That's why the glamorous chandelier begins with something surprisingly unglamorous. Disciplined collection and careful sorting. Over the last 50 years, recycling systems have become increasingly organized, automated, and focused on closing material loops. Today's systems use sensors, cameras, robotics, digital controls, and better logistics to recover cleaner material faster. The next decade may push this further through electrified furnaces, hybrid technologies, renewable energy, and smarter recycling infrastructure. Some European glass projects are already exploring hydrogen, electrification, and hybrid melting as routes toward lower carbon production, but technology alone cannot close the loop if people keep valuable glass outside collection systems. The most advanced furnace in the world still needs the right material arriving at its door, and that simple connection between household recycling and industrial manufacturing is where the real transformation begins. Look closely at this chandelier now, because every sparkling surface carries a story that started somewhere far less glamorous. It began with collection bins, dirty bottles, sorting belts, crushers, furnaces, artisans, machines, and thousands of careful decisions. The heat erased the bottle's original identity, while skilled hands gave the new material shape, rhythm, and purpose. Technology checked the dimensions, quality, structure, and lighting, while human judgment decided whether the final piece truly felt beautiful. And that is the hidden magic of manufacturing, transforming ordinary materials through heat, precision, patience, and imagination. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.